Let's take a look at section 9.1, isometries and congruence. This is from chapter 9, which is on transformational geometry. We skipped a few things, which doesn't mean they're not important. It just means I expect you already know how to do things with coordinate geometry, slopes and distances and midpoints and things like that with x and y coordinates. Now, one of the reasons I restructured this course and chose a different book was to make sure that we did cover transformational geometry. It is one of the topics specifically mentioned by the National Council of Teachers of Mathematics. NCTM wants to make sure you know something about this. So let's get in here, and oh yeah, we are doing stuff in a plane right now. We're doing plane geometry. We're not going to think about 3D stuff. Definitions are a little bit different and a little bit trickier when you have more than just 2 dimensions to work with. So we're going to stick with the with 2 for now. Okay. First idea here in section 9.1 is the notion of a transformation. Now let me give you the formal definition here. A transformation is, make sure, where am I here? Yep. Had some problems here. This is a 1-to-1 function from the plane to itself. So in other words, it takes points in the plane and attaches them or assigns them to other points in the plane. It moves things around. So for instance, a transformation might do something with like this, take this rectangle and turn it that way. Or a transformation may move the plane around so that this rectangle ends up shifting over there. Or a transformation may actually change the plane in such a way that this rectangle changes size and shape. Okay, but it is a way of moving the points around in the plane. Now, we don't really like it if the transformation changes the size and in shape very much. So we're going to stick to an isometry. And an isometry is a transformation that has one particular characteristic. It preserves distance. Okay, so it preserves distances. Well, what you can show without too much trouble is if you have a function in the plane, a one-to-one function that preserves distances, well, it will also preserve angles, and it will also preserve area. So isometry is basically a one-to-one function in the plane that preserves everything that we look at. So for instance, I've got over here on the right a rectangle in black and a rectangle in blue, and there is an isometry, assuming this is the whole plane here, that takes this black rectangle to the blue. It would do a couple of things. It would like shift it down to about there and then kind of rotate it. Okay. So there's an example of an isometry. So it would take, and what you would do to this rectangle, it basically does to the whole plane. It shifts the whole plane down here and then turns it, something like that. Now, some geometry courses are done exclusively in terms of transformations and isometries. I've taught courses like that other places. They're pretty good classes. But what you do when you start looking at congruences is you actually define your congruences in terms of isometries. Now, our book doesn't do things that way, but if you skip on over to page 488, they have theorem 9.5 and 9.6, which would serve as definitions if you did the course in terms of isometries. Two triangles are congruent if and only if there's an isometry that takes one triangle to the other. So, in other words, you have a particular type of function that moves the plane around so that a triangle is moved to another one perfectly. And you can expand that, and I really don't know why the book has two theorems here. Theorem 9.6 seems to me would handle theorem 9.5, but you define congruence in terms of isometries. Now, it may seem that what we're doing here by introducing this new idea of an isometry is just adding an extra level of abstraction to the geometry class that would make it more confusing. But actually, it makes it a little more concrete, because when we look at isometries, I want us to think of rigid motion. Okay. In other words, an isometry is a way of moving things around in the plane in a rigid fashion where you don't stretch them, you don't twist them, you don't cut anything there. So when we say that two figures are congruent if there's an isometry, what we're saying then is two figures are congruent if there's some sort of way of moving one on top of another one in a rigid fashion so that they match up perfectly. And this is the way you explain congruence to kids, is you actually physically show them. I mean, these two things are congruent because I can pick this up and put it down on top of this other figure and have a perfect fit. Now, there are many different isometries, but there are only three basic types. Three basic types. There's translation, rotation, and reflection. And we're going to study them in that order. And every isometry is some combination. And let's think rigid motion. Every rigid motion is some combination of these types of moves. Okay. So we'll look at them specifically, one by one here. A translation. A translation is just where you slide something. You're not changing any angles in terms of rotating it or twist or turning it or anything. You're not doing anything fancy to it. You're just sliding it in some direction for some amount. And a direction and a length are generally what we've described using vectors. And that's what a vector is. It is basically a direction and a length. So in this case, it's this amount from here to here. That's the amount. And then we have some sort of angle. And you can think of that angle as being measured from some direction or so on. But, whoops, where did that come from? But what I've got here is I have a vector, and it's so long, and it moves off in kind of a upper right direction, northeast, or whatever you want to say. Okay, so what this vector does is it tells, I want to apply this translation to the triangle ABC here, so I want to shift everything by that amount. Okay, well, actually, I'm going to draw this vector in here three different places, because if we know where the three vertices of a triangle go, then we know where the rest of the triangle goes. Okay. So if we use vector V to translate triangle ABC, then what we get is this second triangle here, okay, where everything has been shifted this amount in this direction, and we generally label the vertices If this vertex was A that's been moved, I'm going to call that A prime. I'm going to call this one B with a little prime there and C with a prime there. So we just shift things in a parallel fashion. Now, if you look in the book, they have a theorem 9.1 which talks about properties of translation. The short answer, or the short version of 9.1, is translation is an isometry. Period. Okay. Now, let's take a look. I got a couple of translation problems here I've picked out of the end of the section. Problem number 6 is I've got a line segment AB here in the plane. And so I've got X and Y coordinates attached to it. And in part B of number 6, I have a vector. This is my vector V over here. And I want to apply vector V to this line segment. And they don't say draw it. They want to know what are the coordinates of the new points. When you work in a coordinate plane like this, you can describe the vector in terms of coordinates. Okay. So, especially do a lot of this in Calculus 3. Now, I'm going to use a little different kind of notation. Let's use this kind of bracket notation. That's what a vector V does. It goes 1, 2, 3, 4 to the left. So that's -4, okay. And it goes down 1, -1. So what the vector V does when you write it this way, it gives you the change in the X values and the change in the Y values. And this little triangle is what's called delta. And you may have remembered from Calculus 1 or Calculus 2, when you see delta X, that means a change in the X values. So we write the vector this way. Don't use parentheses. Parentheses mean the coordinates of the points. So let's go over here and do that. So here's my point A. Okay. Now let's see. If this is 0, then 1, it's 1 to the left, so it's -1 on the X and a 2 for the Y. And my point B is 1, 2, 3, 4, 1, 2, 3. So it's 4 for the X and 3 for the Y. Okay. Now V tells us what to do. It says change the X values this much and the Y values that much. So -1 minus 4 is -5. 2 minus 1 is 1. This is where the new A is. Okay, I can't draw it on this screen. It's over here somewhere, way over to the left. Okay. B, same thing. We apply vector V to it, which means change the X by 4, go down 4, and change the Y by, decrease the X by 4 and let the Y go down 1. 4 minus 4 is 0. 3 minus 1 is 2. This is the image of B. So there's your answer here. A prime is a -5, 1. B prime is 0, 2. So you shift both of those. That way. Look at the change in the coordinates on the vector. From here to here, it's -4 in the X direction and -1 in the Y direction. Okay. Now I've assigned number 9, and I thought I'd help you get started on this. And maybe I am planning on working it out too much. I don't know. But you want to use a compass and a straight edge. Use a compass and a straight edge, okay, to construct the image of AB under the translation PQ. So everything's going to be shifted this amount. So it's going to be out here somewhere. Okay. Well, here's how you do it. Let's work on moving B. Okay. Draw a line, draw a ray or something, starting at P and going through B. And let it extend here. I don't want to use black. Let's change the color of this thing. I'm in a red mood right now. Okay. All right, what we want to do is to translate, more or less, this vector. I want to slide it up this line to where it's coming out from point V. Now, here's where I'm going to make an attempt to use the compass. Now, the compass tool on this Smartboard program is just absolutely awful. I don't know what people use generally for compasses. I see videos on YouTube, and I'm not sure where they get them. Okay, but take your compass, set the point at P, and the lead, the writing end at Q, and draw an arc that goes down to intersect PB. Okay. Now, without messing with the compass, don't change the radius of the compass there, is scoot the point up to point B and draw another arc going back. Make sure it's at least as big as the one you started with. This distance, B to that arc, is going to be the same as PQ. Now, the next step is what we're doing is making a parallel line here. Is we want to take our compass, put the point where the arc intersects PB, and put the pencil on where the arc intersects PQ, the end of Q, and draw a new arc. Come on, draw. Why aren't you drawing? There we go. Now, without changing the compass, I'm not going to be able to fit. Let me see if I can do this. Make sure I got the right width here. Yeah. Without changing the width of the compass, put the pointy end up here where the arc intersects PB, and draw it so that it crosses there. Now I can mess with it. This new point is going to be G prime, where those two things intersect. From B to B prime is the same as from P to Q. Okay, so that's how you find come on. Whoops. The image of B prime, the image of B. All right, the next basic isometry type has to do with rotations. And this is a that's not a hard idea, but it's sometimes kind of hard to see. So in a rotation, basically what you do is you fix one point in the plane and you spin everything else in the plane around that point. So we're going to fix a point in the plane. I've got a dot down here already, and we're going to call that, where am I here? Let's do green for a little while. We're going to call that point the center of rotation. That's this guy right here. Let's see if I can scoot it up there a little closer. Now, we're going to rotate around that. We're going to turn things around that, and we adopt this convention that, like in trigonometry, a rotation that's counterclockwise is positive. And a rotation that's clockwise is negative. So if we want to rotate this, say, 70 degrees. I want to rotate this, say negative 70 degrees. And let me see, am I getting, nope. Let's rotate it a positive 70 degrees. So if we wanted to rotate this a positive 70 degrees, then I'm going to be doing it that direction. Okay. Let's see what we've got here. So we'll rotate it in a positive direction. That will be this way. By the way, this is a 90-degree rotation. So 70-degree rotation is going to be something kind of less than that. And I probably shouldn't have specified a degree here. If you've got some sort of rotation around a pivot point like this, a center of rotation, you can determine the degree of rotation by looking at the degree of the angle that's made by an original point and its image. So what I've done in this case is I've rotated this triangle in a positive direction, a counterclockwise direction, and I've got to figure out what the angle of rotation is. So we'll get this thing, and these tools on Smartboard don't work real well sometimes. So put the protractor on that point, and where 0 is, the 0 degree is on this line. Okay. And what are we doing? Let's count up. 0, 10, 20, 30, 40, 50. This looks to be a 7, so I've gone from 0 to about 71. A 71 degree rotation. So let's write that down. That's not bad for eyeballing 70 degrees there. Okay, so that's what you do for rotation. By the way, if you measured it, this angle I just measured here, 71 degrees, is the same as that angle. Okay, because that's how far this rotates, and it's the same as the angle from the other vertex. Okay. What happens is the points are just, I should be a little more careful here. Maybe I should put some letters down here. If this is A, then this point down here is the image, A prime. A and A prime are both the same distance from this center of rotation. And the angle that's measured there, OA to OA prime, is 71 degrees, which would be the same as the angle OB to OB prime, which would be the same as the angle OC to OC prime, if you measure those things. Okay, so let's play with some rotation problems from the text. Okay, here's one where we're looking at a kind of like a pegboard or something here, and we want to know if what does it take to rotate P 90 degrees counterclockwise around O. So where counterclockwise is a positive direction, like that. Okay, so it's going to be a 90-degree rotation that way. Well, let's just kind of draw what it probably looks like. Okay, so here, I don't have much space here on my desk, so I'm having trouble drawing things. There's OP, and we want to go 90 degrees this way. So that would be something like that. This is a 90-degree angle. So this point is P prime. Now, Is there any other way to figure this out to make sure we've got it? Well, take a look. You can do slopes. The slope of PO is what? -2. You go down 2 and over 1. So the slope of P prime O should be a negative reciprocal, +1/2. And that's what this is. It's up 1 and over 2. Okay, now we get to problem number 21, and that is using a compass, a straight edge, and or protractor, and we're going to probably need all three of these. Find the -60 degree rotation image of triangle ABC around point O. Okay, now -60 is going to be this way. Okay, so it's going to go around like that. Okay, here's the way I like to do this. When you rotate something around a point, the rotated image, the rotated points are going to be the same distance as the originals. So I'm going to draw circles centered at O. Okay. I'm going to go through point A. Okay. So wherever my new A is, it's going to be on this circle. I'm going to draw the circle through point B. So wherever my new B is, it's going to be on the circle, because rotating doesn't make them go any further away. And draw the circle centered at the point for C. And wherever the new C is, it's going to be on this little circle. Okay, now those are awfully thick, and I don't know why. I can't make the smartboard automatically make things thin, but I can't. So let's draw them. Okay. Now, we need to rotate 60 degrees in the clockwise direction. So I'm going to get this guy up here, and it's a little big, so let's shrink it down a little bit. And we're going to measure off 60 degrees for each one of these points. So put the bottom of the protractor on the pivot point and rotate this around to where I've got A. Okay, so A is there. So go 10, 20, 30, 40, 50, 60 degrees. Let me make a dot where 60 degrees is. That's right there. Okay. And that's for A. So let me make a little note on that. This is going to be A. Now while we're at it, let's go ahead and rotate and get B. Okay, so I'm going to go 10, 20, 30, 40, 50, 60 for B. And that's going to be in this direction. And C is going to be rotated 60 degrees. So it's going to be about here. Okay, and that's going to be, C is going to be somewhere off in that direction. Okay. Let's go. We don't need this anymore. All right, let's draw a straight line from O, a straight line from O to this point. Now, that was for A, so I'm going to put a dot. This is going to be my A prime. Now, 60 degrees over from B was off in this direction. And B is the outermost circle, so I'm going to put a dot there. That's going to be my B prime. And 60 degrees from C was off in this direction. And the C circle is the one on the very inside, so I'm going to put a dot there, and that's going to be my C prime. Okay. So I think we can connect some things here. So I'm going to go from C prime to B prime, B prime to A prime. And the smartboard stuff doesn't want to work right. And from A prime to C prime. So this new triangle is my rotated image, A prime, B prime, C prime. 60 degrees around. Okay. The third type of basic type of isometry is called reflection. Now, in a reflection, we have a line of a reflection. You want to think of that as a mirror. And what we do is we take a point on one side of its line to its mirror image. And basically what that means is, if this is point A, then the reflection of point A, I may not have gone far enough, is it's the point on the opposite side of the line L, okay, that is the same distance from L, so that A prime is perpendicular. So it basically flips it to this point. Now, any point that's on line, say B, stays put in a reflection. Any point that's on the line stays put. So the reflected image is, well, the line segment from A to its reflected image is going to be perpendicular to L, and L is going to bisect. Okay. So let's play with perpendiculars here. Oh, I should say before I forgot to look at my notes. On rotations, if you look at theorem 9.7, it lists the property of a rotation. Basically, it's saying a rotation is an isometry. It preserves distance. It preserves angles. It preserves everything. You can take triangle ABC, cut it out with the scissors, and put it right on top of A prime, B prime, C prime. They're both identical. Okay, reflections here. Like the others, the reflection has a theorem 9.3, and it says properties of reflection, which is basically saying reflection is an isometry. Let's work a couple of reflection problems. Number 30. I have a line L and the points of P and Q. Find the reflected image of Q and P with respect to line L, and describe what this new figure is. Okay, this is really pretty easy. We're just going to, what you do is we start by getting, pick 2 points on line L. It doesn't matter where they are. I'm going to put one there and there. When you're doing these types of constructions, though, it generally helps to pick points that are a little bit far apart. Let's make them red so they show up real well. Things turn out to be a little bit more accurate if your points are kind of far apart. Now, take the circle centered at one of these points on L, going through, let's do Q first. So let's draw some circles. It's going to be centered here, that goes through Q. Okay. Now, take the circle that's centered at the other point on L. Uh-oh. that passes through Q as well. And there's no sense using such a thick marker when you draw circles. Where these two circles intersect is the reflection point of Q. Okay. Do the same thing for P. Take the circle centered at the left-hand point that passes through P. And let's make it thin so that it doesn't get in the way. Now take the circle that's centered at the right-hand point that passes through P. And let's make it a little less. That. Now, where those two circles intersect is the reflection point for P. P prime. Okay, so there's the reflections. Now, describe the figure P, P prime, Q prime, Q. Okay, so let's draw some segments. P to P prime to Q prime, Q to prime to Q, and Q to P. So take a look at this green figure here. What does that look like to you? Well, what it looks like to me is an isosceles trapezoid, where the Q prime is parallel to P prime. Okay. Well, it should be. It should be an isosceles trapezoid. Okay, let me do one more, which is just terribly easy. This is number 43. Now, when it says trace, make sure you really do trace them, because the book's pictures are drawn in a certain location and certain scale so that the problems actually do work. So put a piece of paper over top of the exercises and trace them out. On this one, use a compass and straight edge to draw the reflection line that takes triangle ABC to A prime, B prime, C prime. So there's some line in here that's like a mirror, that the prime side is a mirror image of what's on the other side. And I said, this is a terribly easy problem to do. You need to draw two circles. Draw a circle that's centered at A that goes through A prime. Okay. Now, draw the circle that's centered at A prime. Oops. Draw the circle that's centered at A prime that goes through A. Now, these two circles intersect. Draw the line through those two intersection points. That's your answer right there. That's the reflection line. It does. You could have picked. I could have picked B and B prime, but since those 2 points are so close together, you might not have had a very good line here. Anytime you're out to draw a line, then it helps. You'll draw a more accurate line if the points you plot are far apart. So A and A prime works well. C and C prime works well too. B and B prime, well, the circles you would draw if they went through this would be very small in here, and your reflection line wouldn't be very accurate. Now, the book also mentions something called a glide reflection. Now, a glide, I'm not even going to mention that, other than to say that it's nothing more than a translation followed by a reflection, or vice versa. So I don't know why he put a special definition here, since it's a composition of two isometries. And if the translation preserves distance and reflection preserves distance, then when you do one followed by the other, it's still going to preserve distance. So uh, don't worry about glide reflection things here. Just a composition. Now, uh, if you took linear algebra, these, then you'd be working with coordinates, x and y coordinates, and so on. And these isometries we've got here, the translations, the rotations, and the reflections, can all be written in terms of x and y coordinates. But basically all we're doing is making sure we can visualize them. Oh, by the way, I left something out. I kind of forgot about it. I don't have it written in my notes. When you're doing rotations of 90 degrees, let me, like this guy, let me draw, what if we're doing like in the XY plane? And so we have a point here, and we're going to call it the point A, B. So it's got an x coordinate of A, okay, and a y coordinate of B. Oops. Yep. And oh, we might as well draw this. Okay. Now, what does a 90-degree rotation around the origin do to this? It's going to be that far away. Okay. And it's going to be 90 degrees from this. It's going to look like this, right? What's the coordinate then of this point? Well, the vertical coordinate here was what the old horizontal one was. And now this one, well, B used to go up. This is going to be minus. So 90-degree rotation around the origin takes the point AB to the point minus BA. What does a negative 90-degree rotation do? Okay. What does AB go to in this case? Okay. Well, if you're doing a negative 90-degree rotation, okay, I need to change color here. It's going to be going, actually I got this backwards. I did a negative 90-degree rotation. This one's going to be positive. What I just did up here is negative 90-degree rotation. A positive 90-degree rotation, remember this way is positive, is no. It's right the first time. Negative 90-degree rotation is clockwise. So it's going to be like down here. Okay. So that I have a 90-degree angle here. And if you look and see what the coordinates of this point are, okay, this, if A was the original distance, in positive x direction, this is now, oops, that amount, but down in the y direction. And B used to go up, now it's going to go to the right. So this is going to take AB to the new x coordinate is b, and the new y coordinate is minus a. Okay, think about that. Well, I hope that sets you up for section 9.1. We're going to skip section 9.2, and I will get some 9.3 stuff up before too long. There's some really interesting problems around section 9.3. And we got our next test coming up sometime during this next week. So good luck and get in touch with me if you got any questions.